Today we're going to be looking at 9-2 series and convergence. I had some extra time with this freeze that we're in, so I made a PowerPoint. We'll see if you guys like it. Okay, here we go. So first thing we're going to start with is an infinite series, or simply series. So a lot of times the word infinite gets dropped off and they just are called series. So a series is the sum of a sequence. So a sub n would be a sub 1, a sub 2, a sub 3. The series just adds plus signs instead of commas. To find the sum of an infinite series, consider the sequence of partial sums. So what I mean by that, okay, so the first sum would be the first term. The second partial sum would be the sum of the first two terms. The third sum would be the sum of the first three terms. The S sub n, or the nth term, would be the sum of all the terms including a sub n. So let me show you what I mean by that. Well, let me talk about this first. Okay, here we go. For an infinite series, so when n is going to 1 to infinity, and I'm not sure why I could not get the 1 to go underneath the sum sign. I was able to do it for every other part of this PowerPoint. Anyway, okay, here we go. The nth partial sum is given by S sub n equals a sub 1 plus a sub 2 plus a sub 3 plus ... a sub n, etc. If the sequence of partial sums S sub n converges, then the series is going to converge. The limit of S sub n is the sum of the series. If the sequence of partial sums S sub n diverges, then the series is going to diverge as well. Okay, now let me show you an example. All right, so example 1, we've got the sum of the sequence 1 over 2 to the n. So we're going to look at what numbers we would get. Okay, so here we go. Let's go ahead. Let me get my pen. I want to use black ink. So here we go. This is going to equal 1 over 2 to the first plus 1 over 2 to the second plus 1 over 2 to the third, etc., etc., etc. And the nth term would be the 1 over 2 to the n. Okay, so now let's look at the partial sums. So partial sum 1 would be my first term, 1 half. Partial sum 2 would be 1 half plus 1 fourth. I need a common denominator here. My common denominator will be 4. So this is 2 fourths plus 1 fourth is equal to 3 fourths. My partial sum sub 3 would be 1 half plus 1 fourth plus 1 eighth. Okay, so now my common denominator is going to be 8. So 4 out of 8 plus 2 out of 8 plus 1 out of 8 is going to be 7 eighths. Okay, so now let's look at the sequence of partial sums. So S sub n, okay, is going to be a half, 3 quarters, 7 eighths. So let's look at what we're looking at here. Sorry. So my nth term is going to equal, okay, so in the denominator, I've got 2 to the first power, 2 to the second power, 8 would be 2 to the third power. Look at the relationship between the numerators and the denominators. Aren't they 1 less? So 2 minus 1 is 1. 4 minus 1 is 3. 8 minus 1 is 7. So my nth term, so here we go, S sub n, 1 half plus 1 fourth plus 1 eighth plus ... is going to end up being 2 to the nth power minus 1 divided by 2 to the nth power. Okay, so let's look at this limit. So this sum right here, we'll say the sum from 1 to infinity of 1 over 2 to the n is going to be the limit as n goes to infinity of S sub n. Okay, that's assuming that we diverge. Okay, so again, I'm making a big assumption here because I'm looking and seeing, okay, n to infinity of S sub n, assuming that this is a number, this is going to converge, and then we will equal whatever this number is right here. Okay, so let's figure out what our answer is. Let's figure out what the limit as n goes to infinity of 2n minus 1 over 2 to the nth will be. So if I plug in infinity, I get infinity over infinity, which is a indeterminate form. So I can go ahead and take a derivative of numerator and denominator. And you should be able to do it without doing this. I'll show you here in a second. But, okay, so here we go. This will be ln of 2 times 2 to the n over ln of 2 times 2 to the n. The minus 1 is a constant, so it'll just cancel. And then I've got, those will cancel out. And I have ln of 2 divided by ln of 2, which is 1. Now, because I have the same exponent on the top and the bottom, so I've got n and n in the exponent position, I can look at the coefficients. And the coefficient here would be 1, and the coefficient here would be 1. And 1 divided by 1 would give me 1. Either way, however you want to think about that, that means the sum of this series is 1. So this tells me that the series converges and its sum is 1. So here we go. We would write that this converges, and it converges because the limit of the sequence exists. And we will say that the sum is 1. So that'll be our final answer right there. Okay, here we go. Let's look at the next example. Example 2. We've got 1 over n minus 1 over n plus 1. Okay, so let's look at our S sub n. Our S sub n will be 1 over 1 minus 1 over 2. And that's my first term, so that's a sub 1. Plus my second term would be 1 over 2 minus 1 over 3. Plus my next term is going to be 1 over 3. Minus 1 over 4. Plus my next term will be 1 over 4, right? First, second, third, fourth. Yep, 1 over 4 minus 1 over 5. And then I'm going to keep on going, right? So again, remember, I need to come up with my nth term of my S sub n. So here we go. Let's come up with what we've got here. The 1 will stay there. Minus a half cancels positive a half. Minus a third cancels positive a third. Minus a fourth cancels positive a fourth. So I'm going to have S sub n is going to end up equaling dot, 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 dot. I just don't have any more room to write it over there. 1 minus 1 over n plus whatever the next term is right there. So I'm going to have my 1, because that's what I start with, minus whatever I have for the nth term. Okay, so now we're going to take the limit of S sub n. So we're going to take the limit as n goes to infinity of 1 minus 1 over n plus 1. Now, if I plug in infinity over here, that's going to give me 1 minus 1 over infinity. Okay, well, 1 over infinity is 0, so that's going to give me 1 minus 0, which is going to give me 1. So the limit here is 1. Therefore, it's a number. It's finite. Therefore, this series is converges. And the sum is 1. This is what they call a telescoping series, by the way, just so you have that as reference. We'll talk about more what a telescoping series is. A little bit later, but just to give you a name for it, that's a telescoping series. Okay, let's look at my next example. Okay, so example number 3. So my S sub n is going to be 1 plus 1 plus 1 plus 1. I mean, I don't get anything else. Plus dot, 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 dot. Even the nth term, I'm just going to keep adding 1. Okay, so no matter what it is, I'm just going to keep adding 1. So no matter what the nth is, I'm going to have a sum of whatever my nth term is, right? If I had 15, 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1, eventually it's just going to be my nth term. So if I look at the limit as n goes to infinity, oh, that's a bad arrow. Okay, there we go. As n goes to infinity of n, we get infinity. Is that a single finite number? No, it is not. That does not exist. Therefore, this series diverges. The limit doesn't exist. Therefore, the series is going to diverge. There is no sum, doesn't add to a single number. It's the sum is getting bigger and bigger and bigger, faster and faster and faster. Okay, properties of infinite series. So if a sub n, the sum of a sub n is equal to a, and the sum of b sub n is equal to b, and a sub n, b sub number n are both converging series. So they have to be converging in order for this to work. Then if I have a constant times a sub n, I could factor that constant out, find the series a sub n, just like right here, the series a sub n is equal to a, and then multiply that answer by the constant. Okay, if I'm adding and subtracting two series, I can write them separately. I can find the sum of a sub n, I can find the sum of b sub n, and then I can add or subtract them together. Okay, there are 10 tests for convergence and divergence of series. Okay, that's a lot of tests. The AP test does not test telescoping series and root series. Now, example 2 was an example of telescoping series, so it's not that we can't do it. I have shown you at least one example. I'll show you a couple more as we go through using the other tests. But the tests that they actually test on the AP test are geometric, nth term, p-series, alternating, integral test, ratio, and then direct and limit comparison. So each day of chapter 9, from 9.1 to 9.6, we're going to be looking at 2 of these tests. So 4 more days. Today's day 1. We're going to look at the geometric series and the nth term test for divergence next. Okay, so the geometric series is a times r to the nth power. So the n is what's changing here. The n is in the exponent position. So even though it's not written right here, I have an r to the 0 power. So I start with 0. R to the 0 is my first term. And then my next term is 1. And then my next term is the 2. And then my next term is the 3, all the way till I get to a r to the nth power. So this a r to the n is my s sub n in that series. If r, so r is the base of your exponent. So right here, this r is the base of the exponent, is greater than or equal to 1, we're going to say the series diverges. If r is less than 1, but greater than 0, we're looking at the absolute value here, the series converges. So in other words, the absolute value of r has to be between 0 and 1. We're looking at fractions here, okay? We're looking at decimals. If r is between 0 and 1, then the series converges, and we can use this formula to find the sum. Now, a couple things to notice. First, we have to set our formula up so that n is equal to 0. And then once we do that, a r to the nth power is going to equal a divided by 1 minus r. Okay, let's look at an example. So on our first example, we've got n equals 0. Okay, so that's our first thing for a geometric series. And then here I've got 3 over 2 to the nth power. So I'm going to rewrite that. 3 is my whole number. And then I'm going to rewrite this times 1 over 2 to the nth power. Is that the same thing? Right? So if I rewrote this, this would be 3, 1 to the nth, right, times over 2 to the nth. Well, 1 to the nth is just 1. Doesn't matter how many times I raise 1 to the nth power, I still get 1. So that would be 3 over 2 to the n, which is what I started with. So this is an acceptable way to write that. Okay, so now I'm looking at my A, my R, and my N is in the exponent position. So this is a geometric series. Once I identify that it's a geometric series, I don't have to go through the process of using S sub n and finding the partial sum of the sequences and then taking the limit. Once I recognize that it's a geometric series, I can use the geometric series test. And the geometric series test tells me to look at R. So R is 1/2. And then I need to ask myself, how does R relate to 1? Well, 1/2 is less than 1. So if R is less than 1, we know that the series converges. Okay. Now we're going to find the sum of the geometric series. So we're going to look at our sum formula. And our sum formula is A over 1 minus R. So now I'm going to plug in A, which is 3, divided by 1 minus 1/2. So that'll be 3 divided by 1/2. And I'm going to keep the numerator, so that's going to be 3 times, I'm going to flip the denominator around, that'll be 2 divided by 1. So 3 times 2 divided by 1 is 6. So this series converges with a sum of 6. And there's my answer. Okay, let's look at the next example. Okay, so this problem here, I've got 3 over 2 is in the R spot, right? There's no way I can rewrite that, okay? If I rewrote that, that would be 3n over 2 to the n, which doesn't help me, okay? Because that's still the same thing as 3 over 2 to the nth power. So now remember, this is a geometric series. So in front of the parentheses is a 1. So A is equal to 1. R is the base of my exponent, and the base of my exponent is 3/2. Okay, so again, since I can write it as AR to the n, I know that this is a geometric series. So I'm going to name the test that I'm using. I'm using the geometric series test. And now I'm going to compare R to 1. R is 3/2. 3/2 is greater than 1. If R is bigger than 1, then I know that this series is going to diverge. So it's a geometric series and it diverges. Okay, the nth term test for divergence says that the limit as n goes to infinity of my sequence equals 0. Wait a minute. Gosh, I'm missing something. I'll fix that before I put it in the thing. It does not equal 0. I'm going to fix that before I put it in for you guys to look at. Okay, this does not equal 0. Okay, does not equal 0, then A sub n diverges. If it does equal, I wrote them backwards. No, I hate when I do stuff like that. If it does equal 0, so that's not right either. If it does equal 0, then the nth term test for divergence does not apply, and you could draw no conclusion about the convergence or divergence, and other tests may be done. Okay, so again, the nth term test, if I take the limit and it doesn't equal 0, that series is going to diverge. If it does equal 0, you can make no conclusions. Okay, so let's look at this example. I've got, let's see, what do I have here? I've got 2 to the nth power. Okay, so we're going to do this 2 ways. We're going to use the nth term test, and we're going to take the limit as n goes to infinity of 2 to the nth power, which is going to be 2 to infinity. Does this equal 0? It does not equal 0, right? Doesn't equal 0. Therefore, the series diverges by the nth term test. Okay, so when we're talking about testing for converging and diverging, we're going to want to tell whether it's converging or diverging. Find the sum if we can, if it's converging, and then you're going to want to give the test that you used. Now, that's one way to do the problem. A second way to do the problem is I notice right here that n is in the exponent position. So this looks like AR to the nth power to me, which makes this a geometric series. Okay, for the test for geometric, we look at the R. The base of the exponent is 2. 2 is greater than 1. Therefore, by the geometric test, this series diverges. I get the same result either way. Okay, let's look at the next one. Okay, so now this one, I can't use geometric series anymore. I can't fall back on that because that's not a geometric series. That looks like a ratio to me. So I'm going to look at my limit as n goes to infinity. So this is going to be 3n minus 1 over 4n plus 2. And now remember, the limit as n goes to infinity, we're looking for horizontal asymptotes. So the horizontal asymptotes, if the exponents are the same, we're going to look at the coefficients. Okay, so the coefficients here are going to be 3 over 4. I could also use L'Hopital's. This would be infinity over infinity, which is an indeterminate form. If I have an indeterminate form, I can take the derivative of the numerator divided by the derivative of the denominator. The derivative of 3n minus 1 is 3, and the derivative of 4n plus 2 is 4. 3/4 is my answer. Okay, here we go. This does not equal 0. And if it does not equal 0, this series diverges. And the test that I used was the nth term test. Now, on your test for this section, when I say show your work, this is what I mean by show your work. You said diverges, nth term test. There's the work to prove your nth term test. Okay, so here we go. Let's look at my next series. So we're going to look at the limit as n goes to infinity. Definitely can't use geometric on that because that's not a geometric series. Okay, so I'm going to use the limit of n factorial over 2n factorial plus 1. Now the n factorials act like exponents. Okay, so the highest exponent here is n factorial, and then I've got to compare it to an n factorial in the denominator. So I am going to compare my coefficients. So if I compare my coefficients, I have 1/2. Okay, 1/2 does not equal 0. Therefore, by the nth term test, this series diverges, and we're used the nth term test. Okay, so let's use another one. Okay, that is not a geometric series. There is no exponent in this position. So we're going to use the nth term test. Now notice the n equals 0, the n equals 1 doesn't matter for the nth term test. So the limit as n goes to infinity, doesn't matter whether it starts at 1 or 0, of 1 over n is going to equal 1 over infinity, which is going to be 0. This equals 0. So I can I can make no conclusion. I cannot, I repeat, cannot say that this converges. The nth term test only deals with diverging. If it equals 0, I can make no conclusion about this series. Okay, so make sure that's clear. If it doesn't equal 0, we can say it diverges. If it does equal 0, if the limit equals 0, I can make no conclusion. I don't know what happens with this series. I don't know whether it converges. I don't know whether it diverges. I can make no conclusion. Okay, so let's look at this next example, example 10. Now, before I do anything with this, I have to separate this into partial fractions. So I'm going to say a over 2n plus b over n plus 1. Okay, so now we're going to do our basic equation. So that's 1 equals a times n plus 1 plus b times 2n. I'm going to let n equal 0. So that's 1a equals 1. So a is equal to 1. And now I'm going to let n equal negative 1. So let's see, that'll cancel that out. So that's 1 equals negative 2b. So b is equal to negative 1/2. Okay, so now let's rewrite this. This is going to be the sum at 1 to infinity of 1 over 2n minus 1 over 2 times n plus 1. Okay, so now we need to go ahead and figure out what our S sub n is. Okay, so let's see. I'm going to pull this 1/2 out. So I'm going to have 1/2. And then I'll have the sum of 1 over n minus the sum of 1 over n plus 1. Okay, so if I look at each of these and apply the nth term test, that's going to give me 0, which means I can't use the nth term test. Those are not geometric, so I'm going to go back and use my partial sums. So S sub n is going to equal 1/2 times n is 1, so we're going to have 1 minus 1/2. I'll use another parentheses there. Plus, we're going to have 1/2 minus 1/3. Oh, wait a minute. Look what happens. Halves cancel half. And then the next one, plus we'll have 1/3 minus 1/4. So that's going to cancel that, and that's going to cancel that. Now, if I apply the limit as n goes to infinity, so I'm going to add the limit as n goes to infinity out here. Okay, because I'm trying to find the S sub n, right, what the sum is. So if I take the limit as n goes to infinity, this would be my next term, right? Well, this is going to end up being so small, it'll be subtracting 0. So I'm going to have 1/2 times 1. So this will be 1/2 times I have 1 left, and that'll be 1/2. Since this limit exists, okay, now I didn't just do the nth term test, okay? I did not do the nth term test. I did another test. I used the limit as S sub n is equal to 1. I think my power is coming on. Sorry, not my power, my water. I hear it. Oh, okay, this is so exciting. So therefore we converge. Okay, I have to figure out how to pause this. Alt-Tab. I want to pause for a second. Oh, please pause. Okay, guys, my water came back on. I'm so excited. It indeed works. Ooh, okay, I'm getting back to it. Here we go. I hope that this works. Okay, so I have, let's see, example 10. We did the telescoping series. We had to use our partial sums to find the limit as n went to infinity. So I used neither test. My sum is 1/2. So this series converges with a sum of 1/2. I did not use a geometric. I did not use a nth term, so I don't need to name either of those. Okay, example 11. All right, so I need to find the sum of the series, and then I need to use a calculator to fill in the table, and then I need to graph the first 10 terms of the partial sum. Okay, here we go. So first thing we need to do is find the sum of the series. So I'm going to use partial fractions. So we're going to have 4 over n times n plus 4 is equal to a over n plus b over n plus 4. All right, so let's see what that's going to give me. That's 4 equals a times n plus 4. And that'll be plus b times n. So 4a, if I let n equal 0, is equal to 4, which means a is equal to 1. And then if n is negative 4, that's 4 is equal to negative 4b, and that gives me b is equal to negative 1. So this series becomes 1 over n minus 1 over, what was it, n plus 4. Okay, it's not geometric. If I use the nth term test, I get that it's equal to 0. Therefore, I cannot use the nth term test. So I'm going to go back and I'm going to use the partial sums. Okay, just like we did in the last example. So my partial sums, if I plug in 1, that'll be 1 minus a fifth. Okay, here we go. Plus, the next term will be a half. Oops. I forgot something. Let me get an eraser. Eraser. I want to erase this line right there. Let's get the pen back. Oops. Okay, minus, okay, let's see, n plus 4, 2 plus 4 is a sixth, plus 1/3 minus 1/7, plus 1/4 minus 1/8, plus we've got 1/5 minus 1/9, plus 1/6 minus 1/10, and dot, 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 dot. Okay, so the 1/5 cancels the 1/5. The 1/6 cancels the 1/6. Okay, so I'm going to keep going, and I'll probably cancel out these numbers right here, right? But where did I start canceling? I'm never going to cancel out the 1/2, the 1/4, or the 1/3. Okay, so my S sub n, I'm going to have the 1 plus the 1/2 plus the 1/3 plus the 1/4. That's where I started canceling the 1/5, so I won't have the 1/5. And then I'm going to minus 1 over, now it really doesn't matter what I put here, n plus 1, minus 1 over n plus 2, and there'll be, let's see, 1, 2, 3 terms, so minus 1 over n plus 3. Did I get that right? No, 4 terms, n plus 4. So now if I add a limit here, so if I add the limit as my partial sums go to infinity, all of this becomes 0 over here. So all I have left is 1 plus a half plus a third plus a fourth. Okay, so now I need a common denominator. My common denominator is going to be 12. So this will be 12 over 12 plus 6 over 12 plus 4 over 12 plus 3 over 12. Okay, so let's see, what is that going to be? 12 and 6 is 18. 18 plus 4 is 22. 22 plus 3 is 25. So this will be 25 over 12, which will be 2 and 1/12. So my sum is 2 and a 12. So this series converges, and we have a sum of 2 and a 12. Okay, So now the second part says to use the calculator to fill in the table. So I used some notes here, some calculator notes. Okay, the first thing we have to do is turn the calculator into sequence mode. I am going to make a video of me doing all of these steps in a separate video where I can have the calculator in front of me. So if you get confused, pause right here, go back into Google Classroom and watch the video with the calculator. Okay, so first you're going to turn the calculator into sequence mode, and then you're going to graph. Your n minimum is 1, and then u sub n is going to be the sum of the sequence. This is going to be the formula. So here we go. To get sum, you're going to press second stat, and then go over to math, and you'll see the word sum. To get the sequence, you're going to press second stat and go over to operations. That's your function that we just found, the 1 over n minus 1 over n plus 4. The first n is your variable. The 1 is where we started from, and we got that from right here. Okay, n is equal to 1. That's why we started at 1. And then that's going to be our end value. We're using n because we're going to infinity. We're letting n be whatever variable we want it to be. And then u and minimum is going to be 1. And now we adjust the window. Hold on a minute. Okay, so now we adjust the window. When you press window, you'll see n min, n max. N min is where do we want the graph to start the sequence with? How far do we want n to go? The x min, x max, y min, y max are your domain and range. Okay, so you plug those in, and I'll show you what we get here in a second. Or we can use, to fill in the table values, because that's what we're trying to use the calculator for. We can use the table or use your home screen. Now, what I mean by use the table, you can press second graph and you'll get a table of values. You can set your table set to allow us to plug in 5, 10, 20, 50, and 100 into your table. I've noticed, and again, this just could be my calculator, that it takes a long time. The calculator thinks for a long time when I use this method. If I use my home screen, it's a little faster. And I'll show you what I mean in the video, so you're welcome to go look at that. So on the home screen, I'm going to type into the home screen the sum of the sequence. I'm going to plug in the function. So the function first, and then the variable. So the function, and then the variable. And then I'm going to enter my start value, my end value, and the increment that I'm going to use. Okay, so to get the sum, I press second stat and then go over to math. To get the sequence, you press second stat and go over to ops, OPS, and then look for sequence. The function is this right here. This is your function. Be careful to use the parentheses. Your variable is n. Your start value comes from the n value that we start with up here. The end value I'm going to use in the table, and the increment is going to be 1. We want it to count by ones. So for n is equal to 5, this is what my calculator screen would look like, and this is the answer the calculator would give me. For n is 10. Everything's going to be the same. In fact, I press second enter. I don't go through and type everything over again. I press second enter for everything to come up, and then I just change this 5 right here to be 10, and that's the answer that I get. I didn't change that. Rats. It's not 1.53. That's not right. I will fix that in the PowerPoint. It should be, hang on a second, let me check my notes. It should be 1.7607. So if you're going along with me, that is not correct. It should be 1.7607. Copy and paste got me. Okay, oops. Okay. All right, so now we need to look at what we got from the graph. So that was our first screen. We found the sum of the series. So that's the answer to A. And then if I plug in all of the values for 5, 10, 20, 50, and 100, do you see what these are approaching? So at first it was 1.53, 1.76, 1.09, 2.007, 2.443. So as n keeps getting bigger, looks like we're approaching some 2 value. Look at what we should be approaching. We should be approaching 2 and a 12th. Well, 2 and a 12th is 2.0833. So as my n gets closer to infinity, as my n gets larger, I'm approaching 2 and 1/12. And then I can see the same thing on the graph here. So the window that I used here was 0 to 3. And this was the first 10 terms of my sequence, right? I wanted me to 10 terms. So my x values were up to 10. And do you see what's happening here? Right? My series is approaching a horizontal asymptote of 2 and a 12th. Okay, the bouncing ball problem. A ball is dropped from a height of 6 feet and begins bouncing. The height of each bounce is 3/4 the height of the previous bounce. Find the total vertical distance traveled by the ball. Okay, so the ball starts up here at 6 and it bounces down to the bottom. We're using the x-axis as the ground. And then the ball turns around and bounces back up, but it only goes 3/4 of 6 high and then comes back down again. And then it bounces up again, but only 3/4 of the previous height and then comes back down again. Okay, so it keeps bouncing over and over and over again until it stops bouncing and it doesn't continue to go up in the air. So my first distance is going to be 6. So from here to here is a vertical distance of 6. My second distance is going to be the first 6 plus I had to go 3/4 of the way up for 6, right? Plus 3/4 of the way of 6 down. So this is my up distance and my down distance. So the 6 is still there. Plus, do you see how these are like terms? The 3/4 and the 6, the 3/4 and the 6, they're the exact same terms. I chose to add together the 6's, right? So I have 12 times 3/4. Okay, my next distance. So here we're at, so this is, the red is d sub 1. The red and the green is my d sub 2. And now red, green, and blue will be my d sub 3. So this is the exact same. I went up and I went down. And now I went up again. But I had 3/4 twice, right? So it went 3/4 to 6 the first time, and then 3/4 to 6 times 3/4 of 6. Does that make sense? Like I had to do 3/4 twice to bounce it the second time. And then I had to come down the same distance. So I went up this distance, I had to come down that same distance. So let's rewrite that. This same third distance, I have my 6. I have 12 plus 3/4. That's this first one, just like I had right here. Plus, I have 12 3/4 squared, because I have 3/4 times 3/4. That'll be 3/4 squared. Do you guys notice A, R to the 0, A, R to the first, A, R to the second? And if I did this again, d sub 4, right, would be A, R to the 0, A, R to the first, A, R to the second, plus A, R to the third, because I'd have 3 bounces that I had to do. So this is a geometric series. So once I notice it's a geometric series, okay, I'm going to rewrite this as the sum of a sequence. So my 6, that first distance, plus n is going to be 1, and then I'm going to go 12 3/4 to the nth power. Now, n starts at 1, so that's where my first power, second power, third power, etc. Okay, so this all sounds good to me so far. I've got my a value, I've got my r value. If it's a geometric series, I have to test r. 3/4 is less than 1, so I know that this series converges. If the series converges, I can use the formula to find the sum. But I've got an issue. Oh, goodness. My formula to find the sum of a geometric series has to start at 0. Does this right here start at 0? It does not. It starts at the first bounce. At the first bounce, we go up and back down, right? So if I went back to 0, if I changed this back to 0, I would also be including this part of the bounce right here. And I don't include that as vertical distance, because I didn't throw the ball up before it bounced. It was dropped. So if I back this up to 0, I want to get rid of minus 6, this initial distance right here. Okay, so minus 6. Now I've got my n to the 0. So we're looking good. AR to the n. So now I can plug it in the formula. -6. This whole summation changes to this formula. A is 12, right? A in the 12th position. Sorry, 12 is in the A position. And then 1 minus my R, and my R is 3/4. Okay, so 1 minus 3/4 is 1/4. And then I keep the -6 because that just comes down for the ride. 12, change this to multiplication, flip that over to 4/1. Will be -6 plus 12 times 4, which will be -6 plus 48, which will be 42 feet of total vertical distance traveled by the ball. Okay, so that's your homework for 9.2. Please email me and let me know if you have any questions. Let's see. I need to stop the video. Where do I do that? Here we go. Stop